Well, good evening, everyone. Today we're going to be bringing you lesson 3-2, and I say we because I have here
Kevin. Hey, guys.
and he's going to be helping me out today. And we are going to be talking to you today about prime numbers and prime factorization. So we're going to start out with a little bit of vocabulary. So there are three main definitions that you need. Okay, the first definition is a factor, and a factor is any number, a whole number, that divides another number. So think about what we did last night. Remember we did the divisibility rules?
Yeah.
Okay, so all of that was about what numbers divide other numbers. Those are called factors. So what we really could say is last night we were learning about when is a number like 2, 3, 5, 9, or 10, when is it a factor of another number?
Yeah.
That's all factors mean. Okay, and obviously the book doesn't really say this, but obviously if it's a factor, we want to say that it divides
Evenly.
evenly, right? Okay. All right, so that's what a factor is. Now, based on how many factors numbers have, we classify them as either prime or composite. So a prime number is going to be a number that has exactly two distinct factors, no more and no less. So the only numbers that are going to divide the number are 1 and the number itself. Nothing else can divide it, okay? And they have to be two distinct factors. And distinct means that the two numbers that divide it are different numbers. So, by that definition, Kevin, is 1 prime?
No.
No, it's not, because 1 doesn't, it's divisible by 1 in itself, which is what a lot of people think, but 1 and itself are both the same number, so how many factors is that?
That's 1.
It's only 1. You need two distinct factors to be prime. So 1 is the only number in the whole numbers that fails to be prime because it doesn't have enough factors. So prime numbers always have exactly 2. So therefore, a composite number is the opposite of a prime in a sense. A composite number is a number that has more than 2 distinct factors. Okay, a great example of a composite number would be like 12, because it's divisible by 1, it's divisible by 12, by 2, 6, right? And also 3 and 4. So actually 12 has 6 different distinct factors. So definitely not prime. And that's what we call composite. All right, so we got 3 definitions: factors, prime, a prime number, and a composite number. Okay, so make sure you remember those. You might want to come back to this slide. You might even want to write this down in your notes. What a factor is, what a prime number is, and what a composite number is. All right, well, let's see how you use these. All right, so let's do some examples. I'm going to write down a whole bunch of numbers here: 24, 87, 73, 101, 54, and 57. And what Kevin and I would really like you to do is pause the video and take all 6 of these numbers. How many numbers?
6.
6 of them. And go ahead and take your best guess of whether the number is prime or composite. And an easy way to do this is if you think a number is composite, then write down some number that divides it other than 1 and itself. Okay? And what I would strongly recommend that you do, every single one of these, for the most part, if you use the division rules from yesterday, the divisibility rules, you should be able to use just those. Really simple. Really, it's really 2 rules. I say it's 5 rules, but really it's 2 rules. And if you use those 2 rules, you ought to be able to tell almost immediately whether these numbers are prime or composite. So go ahead and pause the video right now. For each of these, write down prime or composite, and if you think the number is composite, write down some number that divides it. Okay? And if you want to really knock yourselves out, write down all the numbers that divide it other than 1 in itself. All right, we'll see you in just a second. All right, so Kevin, 24, what do you think? Prime or composite?
I think that's composite.
It's definitely composite. There's no question about it. We don't have to go any further than look at the last number.
Yeah.
It's even, so 2 divides it. What else divides it? I don't know. Let's see. 3, 4, oh my gosh, 12, 8, 6. Let's see. 2
1.
and 12. Yeah, 1 and 24 divide it. We won't write those down, though. 2 and 12. 3 and 8, 4 and 6. Yep, I think that's all the different numbers to divide. But look, it's got 6 factors plus 1 and 24. So it actually has 8 different factors. Definitely composite. Okay, what about the next one? 87. Well, did you add up 8 and 7? 8 plus 7 equals what?
That would be 15.
15.
Right? Yeah.
And if it adds up to 15, then we know already it's divisible by 3, so it's definitely composite. Okay, remember that from yesterday.
Yeah.
So it turns out that 87 is almost prime. 1 and 87 go into it. Also 3 and 29. That was a tricky one. But 3 times 29 does equal 87. But the 3 wasn't that hard. Just using the rule from yesterday, we can tell that that is composite. All right, now let's take a look at 73. All right. This one ends in a 3, so it's definitely not even. It's not divisible by 2. It adds up to 10, so it's not divisible by 3 or 9. It's not divisible by 5 or 10. So by the rules we did yesterday, this one looks like it's probably going to be prime. And I would tend to agree. I do not think that there are any numbers that divide 73 other than 1 and 73. And since it only has 2 distinct factors, it is a prime number. The next one also, I think, falls in that category. I can't think of anything that divides 101. It's not divisible by 3 or 9. It's not divisible by anything even. We could try the 7 trick, but if I rip off the 1, double it, and subtract from 10, I get 8. And 7 doesn't go into 8, so I don't think anything's going to go in. I think that one is prime as well. All right. What about 54? What is 50? First of all, it's even, right?
Yeah.
Plus, what is 5 plus 4?
That's 9.
That's 9. So that is definitely...
That's definitely composite.
Definitely composite. And I can write down a whole bunch of different numbers. You only had to write down 1, by the way, but the numbers that go into that, I know 2 goes into it, 27 goes into it. We just proved that 3 goes in. It's going to go in a total of, let's see, it goes in 18 times. Let's see, does 4 go into it? No, 4 does not go into it. But 6 and 9 both go into it. 6 times 9 is 54. So we got a lot of different factors for 54. What about 57?
I don't think that would be composite.
It would be. What is 5 plus 7?
12.
It's 12. And so automatically, without going through everything that divides it, we know that 3 goes in. It goes in a total of 19 times. Now that one's pretty close. If you didn't see 3 times 19, if you didn't know the 3 rule to add the 5 and 7, you probably would think 57 is prime, because you probably wouldn't test to see if 19 goes into it. And honestly, those are the only factors of that one. So both 87 and 57 both look like they could have been prime, but they actually turned out to be composite. All right, so you need to be able to look at any number that you're given and tell whether it's prime or composite. And the main thing you're going to do this is a great lesson to come after 3-1, because 3-1 was all about divisibility rules, and that's exactly what you're going to use here to tell whether something goes into another number, to see if there's any other factors. Okay, I will say one more thing that's a little bit tricky.
7.
So in addition to the divisibility rules, so Kevin and I were talking about this, and in order to be prime, you can't be divisible by anything other than 1 or yourself, which means none of the even numbers can be prime, because all of the even numbers are automatically divisible by 2.
Yeah.
Okay, and we also talked about how none of the numbers that are going to be prime can end in a
5.
A 5. Like think of things like 15, 25, 35. They're all divisible by 5. So in order to be prime, really, the only possible numbers that your number could end in, we'll put them down here in the corner because we're kind of out of space, would be
1, 3, 7, or 9.
Yeah, 1, 3, 7, or 9. Now, that doesn't count the single-digit ones. So for less than 10, we do actually have 2 special prime numbers. Which 2 prime numbers stick out as kind of special to you, Kevin?
Those would definitely be 2.
Yep. 2 is the only even prime number.
And 5.
And 5. It's the only prime number that ends in a 5. Yeah. And it doesn't really end in a 5, it is 5. Anything after that will be divisible by 5, and anything even after 2 is divisible by 2. So 2 and 5 are special primes because they pretty much mess up all the rest of the evens and all the rest of the multiples of 5.
They killed the system.
They did. So, and they make the system. So if you have a number and you don't know if it's prime or composite, unless it ends in 1, 3, 7, or 9, don't even worry about it. It's automatically composite. Now, just because it ends in 1, 3, 7, or 9, let's go back a screen, doesn't automatically mean that it's composite. So here are some examples. 87 ended in a 7, but it was still, I'm sorry, it doesn't mean that it's automatically prime. That one actually turned out to be composite. 101 actually ended in a 1, but that one was prime. 57 ends in a 7, and it's composite. Okay. Oh, and 73. So these 2 examples are ones that end in 1, 3, 7, or 9 that were prime, but both the 87 and the 57 were examples that were not. Okay. So, but you don't even bother checking unless your number ends with one of those numbers. Okay, so that's what prime numbers are, and what we're going to do next is we're going to talk about prime factorization. So if a number is prime, there's not really much you can do to break it down. It's just 1 times itself, so you're already done.
Yeah.
But if a number is composite, what we can do is we can do factor trees, and we can break, these are called prime factor trees, and what we do is we break the number down into numbers that go in, that multiply together to give you 60, and we keep going until we get prime numbers. And when we get all the way to the bottom, when we get to the prime number, you can actually circle those. And you know what, I'm going to change color since this is a tree. Why don't we do this in green, and we'll do it. Yeah, all right, so we'll start with the trunk. We'll make it yellow. But what are 2 numbers that multiply together to give you 60?
30 and 2.
Okay, 30 and 2.
But 2 is prime.
And 2 is prime, so we're going to circle that. Okay, now 30 could break into what, like 5 times 6?
Or 15 and 2.
Or 15 and 2. Let's do 5 times 6, and 5 is prime, so we'll circle that.
Yeah.
And finally, the 6 breaks into 2 times 3.
And those are both
Now, as you could tell, there are other ways we could have broken the same number down. However, now when you're done, you'll always get the same prime factorization. So this one has 2 times 2 times 3 times 5. And we can write that a little bit easier. If we use exponents that we talked about, that's actually 2 2's. So we could write that as 2 to the second power dot 3 dot 5. And that is the prime factorization. Now that's not the only way to get the prime factorization of 60. We're going to do 144 next, so I put that up there so I have enough room. Let's do 60 again, and let me show you a trick. Usually if you break the number down into 2 numbers that are closer together, you'll get a little bit more balanced tree. So let's say instead of 30 and 2, what if we'd started with 6 and 10? Whoa. Then the 6 will break down into 2 times 3, and the 10 breaks down into 2 times 5, and look at which prime numbers we get. Don't we get the same ones? We get 2 2's, a 3, and a 5. So we get the same prime factorization whichever tree I do.
Yep.
Okay? And so if you don't make any mistakes, that will always be the case. So that's this down here in the box is actually the prime factorization, not the tree. The tree is how you get there, but the actual answer is the prime factorization. Okay, I've never actually used brown, so let's go ahead and use a kind of a brown since it's autumn.
Or tannish.
We'll stay with the whole tree, yeah. We'll stay with the tree idea. So what are 2 numbers reasonably close together that give you 144?
I would go with, let me think. Like
That's actually a perfect square, isn't it?
Oh my gosh.
We could do 12 times 12.
That is, isn't it?
So 12 times 12, or 12 dozen, breaks 144 down. And now look, all we got to do now to finish this, what's 12 break into?
6 and 2.
6 and 2, and the 6 can break into 2 times 3.
Yeah.
Okay, this one over here, let's do it a little differently. Let's break it into 4 and 3.
Oh.
That'll also give you 12, and the 4 breaks into 2 and 2. It doesn't matter.
Yeah.
You notice on the left side I get a 2, and a 3, and on the right side I get a 2, and a 2, and a 3. So all told, I'm going to have to actually erase this bottom because I'm running out of room here. So let's erase those. And the prime factorization for this one is going to be, I'll make this a little bit darker. Let's count all the 2's. There's 1, 2, 3, 4 to 2, so that's 2 to the 4th power.
3's.
And I see,
second.
Yep, and 2 3's, so we'll put a dot, and 3 to the second. And so if you were to take 2 times 2 times 2 times 2 times 3 times 3, you'd end up with 144.
Yeah.
Okay, so the prime factorization for this one, we'll put a box around it again, is 2 to the 4th times 3 to the second.
Yep.
All right, so let's practice a couple more questions. And so what we want you to do on these ones, here are the directions. And again, we want you to pause it and then answer these. And for each question, you're going to identify the number as either a prime number or a composite. And if it's composite, we want you to break it down into its prime factorization. Obviously, if it's prime, the prime factorization is just the number itself. So the numbers we're going to give you are 360, 91, 83, and 210. So go ahead and pause now and resume as soon as you have either decided that these numbers are prime or composite, and if they're composite, find the prime factorization. Okay? Go. All right. I think we're ready to go. All right, the first one is obviously composite, right? It ends in a 0, it's even, it's got all kinds of things that divide it. I would break it into 36 times 10, and then 36 I'd probably break into 6 times 6, and the 6 breaks down into 2 times 3.
We're out of room here.
We're way out of room. And the 6 also breaks into 2 times 3, and the 5 breaks into 2 times 5. Oh my gosh, we fit it in.
Okay, we should
so
need
it looks like I've got 1, 2, 3 2's. So that's 2 to the 3rd. I've got 2 3's.
I was about to say don't bother writing the prime factorization, but that's just going to leave us with less room.
I know, but that's okay. We'll squeeze it in there. And there it is. So, so that's what you should have done on 360. So do a factor tree. Your factor tree may not look exactly the same as Kevin and mine, but it should end with the same numbers. And you notice that this time, Kevin, I did not circle the prime numbers just because it was getting so tiny. I don't think you'd be able to read it if I did. But normally we circle the prime numbers when we get to the bottom. Whoopsies. When you get to the bottom, like we did on all these. Notice we circled all the prime numbers. Okay, so let's go ahead. Let's go back to where we were. All right, number 91. Looks like it's prime, doesn't it?
It looks like it.
It sure does.
I don't trust it.
I don't blame you. That's very smart. It is actually not prime, and here's the trick. Now you really had to play around with this to get it. So if you put prime, don't feel bad. But remember the trick. If I take the 1 off, I rip it off and I double it, I get 2. Ooh. 9 minus 2 is 7, and 7 is divisible by 7. You might not realize it, but 91 is equal to 7 times 13. It's probably the hardest number you're going to run into. It is not prime, although it looks like it is, and we don't usually do divisibility rules. You guys have an advantage over any class I've ever taught before because we actually did the rules for 7 and 13. In fact, if we did the 13 rule, we would have taken the 1, we would have ripped it off, multiply by 4, and add it to 9, and sure enough, we get 13. So those two rules actually work on 91, and so it is not prime. And actually, I didn't really draw this as a tree, but if I did, I'd get 7 and 13. And that is the prime factorization. So I'm kind of sorry about that one. That's kind of sneaky. So don't feel bad about that. But hey, look, you just saw the hardest number I can think of, and now you can be on the lookout for it in the future. 91 is not prime.
I've never trusted 9s.
I don't blame you. All right, 83, if we add up 8 and 3, it adds up to 11. Let's see. If I try the little 7 rule, I get 1. That doesn't work. 13 doesn't go into it. I think 83 is actually the real deal. I think it is prime.
For once.
If I'm wrong, that gives you a chance to get a bonus point, but I wouldn't spend a lot of time on that. I'm pretty sure we're right about that. That one is prime. But 210 is definitely not prime, and I'm not sure we're going to be able to fit this one in. So I'm going to write really small and make my tree really narrow, but this is 21 times 10, and 21 is 3 times 7. Well, that wasn't that bad.
Don't even bother.
I could actually circle that.
Oh, okay.
And then the 10 is 2 times 5. And that's actually kind of interesting. Oops, it's a little hard to read now. That was a 7, and this one here is a 2. But I get a 2.
That's smaller than I expected.
Yeah, and I kind of thought it was going to go a couple extra steps too.
Yeah.
So it's 2 times 3 times 5 times 7. In fact, that one's kind of interesting because those are the first 4 prime numbers. 2, 3, 5, and 7. If you multiply the first 4 prime numbers together, you get 210.
We found another special number.
That is a very cool number.
Yes,
and that is the prime factorization of that one. So we are good to go. All right, so we're going to wrap things up because we're at 17 minutes. Time flies when we're having fun.
Sorry.
So we're going to go back to the old Despicable Me and a Minion. And the Minion would like to say that thanks for watching.
Okay.
So
and don't worry, all you guys. You're special too, especially you, Logan.
There you go. All right. So you all, thanks for watching our video, and we will see you in class tomorrow. Take care. Bye.